Hello everybody, welcome. This is May 2023, paper 2, and it's from time zone 1. Alright, final question on paper 2. Should be a good challenge. Let's have a look. Maximum mark is 17. A large closed container in the shape of a half cylinder with a rectangular lid is to be constructed with a volume of 0.8 meters cubed. The container has a length of L meters and a radius of R meters. Part A asks us to find an exact expression for L in terms of R and pi. So we want to write L in terms of two other, one is a variable and one is a constant. So in terms of R and pi. So whenever we say in terms of, it means that we are having L on one side and then we'll have R and pi on the other, and maybe R and pi will be multiplied by something or divided by something, but we want L on one side and we want to write L in terms of R and pi in some kind of combination. Maybe we're going to square one, divide one, so on, so on, so on. Alright. So find an expression for L in terms of R and pi. So let's see how these things are related. What do we know? What do we know? What do we know? The only value that they really give us is the volume, and it's equal to 0.8 meters cubed. Okay. And this pi should indicate that we're going to be dealing with something with circles. So if we want to write in terms of R and pi, how could we write this out? What do we have? We have a cylinder, but really only a half cylinder. So let's go into the formula booklet and find the formula for the volume of a cylinder. Okay, so here we are. Here's our formula booklet. This is going to be in geometry and trigonometry. And let's find the volume of a cylinder right here. And it's equal to pi r squared times height. R is the radius, h is the height. Okay. Pi r squared times height, that's the volume of a cylinder. Okay, so we know that the volume is equal to pi r squared times height. But we don't have the volume of a whole cylinder here. We just have half of a cylinder. So we can write V half, but I'm going to write it just in terms of what we have here. So our volume itself is equal to 0.8. So we know that the volume of this whole cylinder is going to be equal to 0.8. And as an expression, it's going to be pi r squared times h, but we only have half of a cylinder. So that's going to be our volume of a, let's say a half cylinder, this V sub h, volume of a half cylinder. And what is the volume of our half cylinder? It's equal to 0.8. So let's write that out. 0.8 is equal to pi r squared times h over 2. You might say, okay, well, how does that get us closer to this L? Finding this L. When we work this out, when we use this volume of a cylinder formula, we had this h here. But remember, if we're talking about the volume of a cylinder, let's draw a cylinder here, for example. The volume is going to be given by pi r squared, or area of the base, this is r right here, times h. And all we've done for this cylinder is we've laid it on its side and we've cut it in half. So the distance from the bottom to the top of the cylinder, sure, when it's on its base right here, it's the height. But if we lay it on its side, then now this becomes the length. So the height of the cylinder essentially is L. So let's go ahead and write that in. Okay. So really it's pi r times L times L times L. Okay, Oops, I gotta get rid of that. Alright. So now find an exact expression for L in terms of R and pi. And this is actually going to be a fair bit of algebra, actually. More than you might expect, potentially, on an AI paper. So we don't want this 2 here. This is pi r squared divided by 2, but we don't want pi r squared times L divided by 2. We want L all by itself. So how can we do that? Let's get rid of this divide by 2, and to do that, let's multiply both sides by 2. So we're multiplying both sides by 2. 2 divided by 2 equals 1, so they kind of cancel out. They do cancel out. And now we have 1.6 is equal to pi r squared times L. Remember, pi r squared is just the area of the base. The volume is area of the base. This is area of the base times height, which when we have the cylinder on its side, this is just our height. And now the last step to get L all by itself, what do we have? We now have L being multiplied by pi r squared. So to get rid of this pi r squared, we don't want it multiplied, we divide both sides by pi r squared. Pi r squared. And now, again, pi r squared divided by pi r squared, anything divided by itself is just equal to 1. So this pi r squared just equals 1. And now we have L is equal to 1.6 over pi r squared, where L is equal to 1.6 over pi r squared, as we would read it. Okay, so that is, to be honest, quite a challenging question, especially for a 2-mark question, and a significant amount of actually algebra. Okay, so there it is. L is equal to 1.6 pi r squared. We have an expression for L in terms of r and pi. So L's on one side, and pi and r are on the other. Okay. So remember, I guess now the time would be to say paper 2 questions, especially something like this, 17 marks. Look for the entry points. This is an admittedly, quite challenging question involving a fair bit of algebraic manipulation. The mark scheme awards a mark for setting up this 0.8 times pi r squared times L. So just working with the volume of a cylinder, recognizing that L, or the height rather, corresponds to the length in this case because it's on its side. This would give you 1 out of the 2 marks. So potentially not too bad. Algebraic manipulation is challenging. Essentially we want to use opposite operations. So if we're dividing by 2, we see this, everything is divided by 2, we want to multiply by 2. If we're multiplying by pi r squared, we want to do the opposite and divide both sides by pi r squared. End goal is to get this variable, this L, all by itself. Okay, let's move on. The container will be constructed using 2 different materials. The material for both the curved surface and the rectangular lid of the container costs $4.40 per square meter. The material for the semicircular ends costs $P per square meter. Okay. So, let's see. The container will be constructed using 2 different materials, curved surface and the rectangular lid. So what is the curved surface and the rectangular lid? The curved surface is of course this right here, and the rectangular lid is this. That doesn't show up too well, but there it is. Maybe I'll write it here as well. It's a little better. So this is the rectangular lid right here. I hope that's coming through okay. That's a little better. And then of course the curved surface along the edge. I hope you can see that. Yeah, that's fine. And this is going to be $4.40 per square meter. And the semicircular ends, that's these right here. This costs P p dollars per square meter. We don't know yet. So I'm actually going to write this out in a different color just to make it a little more visible. These are the curved surface and the rectangular lid. Okay. Alright. The cost C of the materials to construct the container can be written in terms of R and P. So again, we have this in terms of R and P, where P is greater than 0 and R is greater than 0. So what does that mean? Radius is greater than 0, and P, the price, is as well greater than 0. Okay. Show that the cost is equal to 7.04 r to the negative 1, 14.08 over pi times r to the negative 1, and then p pi r squared. You might say, geez, that's very intimidating. You know, how do we go about this? Well, actually, we'll work this out. But remember, things are compartmentalized. We have a 3-mark question right after, which is just asking you to derive this, and we already have our exponents as a negative 1. So remember, this, jumping ahead a little, this 1 over x, we wrote as x to the negative 1, because it's not possible to derive this as it is. We first need to convert it to this form where we get our exponents, a negative exponent. No variables in the denominator allowed. We've already got this converted. So this is a nice kind of, you know, generous question. Not generous, but it's very manageable. So remember that the questions themselves on a paper 2 are somewhat compartmentalized. Alright, so show that C is equal to 7.04 r to the negative 1, and so on, so on. What does this r to the negative 1 mean? It means 1 over r. So we can go both ways in this case. R to the negative 2 is equal to 1 over r squared. And if we get something like 1 over r cubed, this is equal to r to the negative 3, and so on, so on, so on. That's what that r to the negative 1 means. Okay, so let's try to work this out. Need some good space. Here's B. Okay, so what do we know? Cost is 440 per square meter, and that's for the curved surface and the rectangular lid. So let's write out cost equals, and then let's write it out in terms of curved surface plus rectangular lid, that's all going to be equal to 440 per square meter. So curved surface times rectangular lid times 440. So if we know the area of this, we can multiply it by 440. And it's also going to be equal to, and we've got a half semicircle right here. And these are our, let's just call it semicircular ends. I'm going to write S circular ends. And if we find the area of that, then we can multiply it by P, and that should give us our cost. Okay. So let's go ahead and work this out. So the curved surface, what is the surface area of a cylinder? This one's actually in your formula booklet. I'm going to go there real quick, and we'll speed up this one, I suppose, as well. So where are we? The curved surface of a cylinder. So geometry, trigonometry. Here we are. Area of a curved surface of a cone. We want the curved surface of a cylinder. Okay, let's see. Here we go. Area of a curved surface of a cylinder, and it is 2 pi r h. R is the radius, h is the height. 2 pi r h. Okay. So let's write this out. Area is equal to 2 pi r times h. And remember, h in this case is the height, but since our cylinder is itself on the side, this is actually equal to L. That's the curved surface, 2 pi r times L, plus the rectangular lid. The rectangular lid is just a rectangle, and it's r times L. So this is just r. Actually, one sec. It's not exactly just r times L. This is r, and this is r. So total distance we need to go is 2r. So if we want to find the total, if we want to find the area of this rectangle, a rectangle is of course length times width. The dimensions of this rectangle are 2r times L. Alright. 2r times L. And then we have plus the semicircular ends. And we have, this is given to you in your formula booklet of course, area is equal to pi r squared. But we don't have a full circle, so each of these are just, well, half. We have half of a circle, so it's pi r squared over 2. But we do have 2 halves of a circle, so essentially we have a full circle. And the area of a full circle is just given by pi r squared. So we have pi r squared. I just realized that I forgot something. This is the total area right here, and we need to again multiply this by $4.40. And here for our curved surface, or sorry, our semicircular ends, this we're just going to multiply by p. Okay, so good challenge so far. This is area of the curved surface, 2 pi r times h. H is itself L. Rectangular surface is just the dimensions of a rectangle, 2r times L. This is the total area right here, and it is 440 per square meter. This is our 2 semicircular ends. 2 half circles make a whole circle. This is our area right here, and it costs $p per square meter. Okay, so we're actually almost there, but if we look at the original formula, it's just in terms of r. There's no L, there's P, that's okay, so this should be able to stay. The r's should be able to stay, but we want to get rid of these L's right here. And remember, oftentimes, I've said this a few times, that the IB will often ask questions that lead into something else. They won't ask you something as a kind of piece of trivia or just to test a discrete skill. That will often lead into something else. And we found earlier that L was equal to 1.6 over pi r squared. And remember this equals, whenever we see equals, it's essentially an is. L is equal to 1.6 over pi r squared. L is equal to 1.6 over pi r squared. L is 1.6 over pi r squared. So what does that tell us? That means that wherever we see an L, since L is 1.6 over pi r squared, we should be able to substitute this value for L. So let's go ahead and do that. So all of this is equal to 2 pi, and then L is equal to 1.6 over pi r squared. I'm actually going to use a color, 1.6 over pi r squared, because that's what L is. L is equal to 1.6 over pi r squared. We should be able to just substitute pi r, whoops, let me erase this, 2 pi r times L, and then L itself is right here, 1.6 over pi r squared, plus 2r, which is fine, but then we want to multiply and substitute, get rid of this L, and replace it with pi r squared. All of this, once again, multiplied by 440, plus, and then this can stay as it is. This is just pi r squared, no L's or anything like that. Alright, now we have to expand. Actually, to be honest, I'm going to try to look up and show you the mark scheme. I believe I have it here. If I don't find it within 10 seconds, then I will go on. Let's see, is this it? This is... This is not it. I'll try one more. One more. There's a paper 1. We'll try once more. I don't think this is it. Okay. I'm going to show you on the larger screen then. So here's the mark scheme actually right here. So after we write that out, there's some method marks right at the beginning. So area with L is replaced by 1.6 over pi r squared. And the question is, like, we've got this rather messy looking formula right at the end. And the question is, like, do you have to expand it to show that, hey, one thing is equal to the other? You don't actually. I mean, after all of the expansion, it's just a way to confirm that, yes, in the end, cost is equal to all of this business. So we have 440 times pi r, 1.6 over pi r squared, plus 440 times 2r, 1.6 over pi r squared, plus pi times pi r squared. Sorry, p, the price for that rectangular lid, times pi r squared. So you don't actually need to expand it. You just need to write it out after substituting L in for this. So here's the cost given by each of these formulas, which is kind of manageable, I think. And then L, if you're able to get that L at the beginning, or find the value of this length in terms of pi and r squared, substituting L for this, and then we're writing out the final value. Challenging question, no doubt, but I guess the positive thing is we don't need that final expansion to show that it all equals each other. Okay, let's go back to the document. Okay, so I don't think I'm actually going to expand this. Do I want to? No, that's okay. I think that's fine. After that, it leads to 7.04 r to the negative 1 plus 14.08 over pi r to the negative 1, once again, plus pi, or sorry, not pi, p pi r squared. Okay. Alright. Certainly a challenging question. Part C is asking you to find the derivative. So change in cost over change in the value of r, the radius. So as we stretch out the radius and make this kind of wider at the bottom, or shrink it, how does that change the overall cost of these cylinders? So remember, dc over dr is the same as c prime, just like dy over dx is equal to y prime or f prime of x. Right? All of these things notationally mean the same thing. So dc over dr is a c prime. It means we want to take the derivative. So let's go ahead and take the derivative. Here's c. C is equal to, I'm actually just going to borrow this right here. There we go, that's good. And now let's take the derivative. Formula booklet has our derivative. I'm going to write it out real quick. If f of x is equal to x to the power of n, this is given in your formula booklet. Derivative is equal to n times x to the n minus 1. So we multiply by our exponent, and then our exponent reduces by 1. Let's give it a try here. C prime, which is the same as dc over dr, is equal to, let's take this negative exponent, multiply it out in front. We now have negative 7.04 r. R used to be negative 1. Now we're going to take away 1 from this, and now it's going to be -2, plus, this is just some number. This is just some number. Pi is not a variable. Pi, remember, is equal to 3.1415 and so on, so on, so on. That's all I remember. 3.1415. Infinite number of digits, of course. So this is just some number. We don't need to do anything with this pi. It's just some number. What we need to focus on is this r value right here, this variable. And in this case, we just want to do the same thing. Take this r, multiply it out in front. And so now all of this business, this 14.08 over pi, is going to be multiplied by a negative. So this will actually become all negative. So negative 14.08 over pi. R used to be -1, now it's -2. Plus, and now again, this is what makes, I think, this question more challenging. What do you do with this p? What do you do with this pi? P, remember, is the cost. We're not taking the derivative in terms of p, the cost, or anything like that. P is the cost. P stands for some number. It's some dollar amount that we don't know yet. It's fixed though. It's not going to change. And if it's not going to change, it's just a constant, like a number. And so we don't take the derivative in terms of p and r. It's just some number. All of this is just some number. R is the thing that changes, and it's what we want to take the derivative of. So once again, dy dx, take the derivative in terms of x, just deal with the x. dc dr, take the derivative of r, everything else leave it as it is. Just focus on the r in this case. Okay, so let's go ahead and take the derivative here. So focusing on the r squared, multiply it out in front, this becomes 2p pi. So we just took this exponent, multiplied it out in front. It used to be a 2, we take 1 away from it, and now it's 1. There it is. Challenging question, but I think it's a good question. It's a good question. Okay, let's continue on. So there's our derivative, and it's a good 3-mark question. Alright, I think this is rounding out to the bottom. There's just a little more after. Okay. Alright. The cost of materials to construct the container is minimized when the radius of the container r is 0.7 meters. Find the value of p. Wow. Okay. The cost of the materials to construct the container is minimized when the radius of the container r is 0.7 meters. Okay. So, what can we do? The cost of the container r is minimized when r is equal to 0.7. So when r is equal to 0.7, the cost of the container is minimized. I want to go back to the calculator and just give you some kind of conceptual understanding of what's going on here. This is our original cost function. Actually, sorry, back to the document. 1 sec. We have an equation for the cost, and we've also got an equation for the derivative, that is to say the change in the cost as we vary r. So remember, the derivative is just a change, momentary change at a given point. So let's actually put in this cost function, and then we'll get an idea of the change in cost through time. So let's put that in on the calculator right here. So we have 7.04 r, actually, sorry, we're going to need x to the -1 plus, set up a fraction, 14.08 over pi, and then this is again going to be multiplied by x to the -1, and then the problem here is we don't know what p is. We don't know what p is, so we can't just simply do pi times r. So we can't just simply do pi times x squared. Because we have two variables. We have two variables, and that's a problem. So, I mean, as we... what do we know? We don't know the cost. We don't know... We do know the final radius, but we don't know the price. So what's going to be challenging here is that we have the final cost we don't know. We just know it reaches a minimum. We know that the R value is going to be 0.7, but we don't know P, so we still have too many unknowns. So that one, we're not even going to be able to look at the function and see how it changes. We can get an idea, if we erase this, we can get an idea of what this might look like, this cost function, if the price were equal to $1, and so on and so on. Maybe even not too much of an idea. And then we could put in $2 and $3 and $4 and so on for different values of P, but this isn't going to be a way to solve it. We have too many variables. We don't know P. We can't substitute it. So what that means is we're going to actually need to use our derivative. So here it is. Let's go and bring this to the next page. I'm going to copy this, and then let's bring it here. Okay. So the cost of the materials to construct the container is minimized when the radius of the container is equal to 0.7. It's a good question. I think it is. So I'll draw an axis, a set of coordinates here, and what do we know? Something is minimized. If we have some function like this, actually going back to the calculator for a sec, we see our function as it looks like we're going to have an infinite amount of cost if we make our radius like super small. Like even though we don't have P here, the cost, if P is equal to 1, for example, the price of this rectangular lid is equal to 1. The cost for a very small radius is going to be massive. But there's going to be a point where we have a minimum right here. And then of course as we increase the size of the radius, the cost as a function of the radius, the cost starts to increase. It increases some more. So let's even work with this. So let's go back to the document for a sec. And we have cost as a function of the radius right here. And this is what we have for some value of P, but we don't know the value of P yet, so we can't actually use this function. But this is kind of what our function looks like. And remember, it can't be negative, so we're just dealing with this positive area where R is greater than 0, right? So just this side. And what do we know? The derivative itself gives us the slope of a line at a point, or the slope of a tangent line at a given point. So if we're looking at this point right here, for example, we have a negative slope. And if we look at this point right here, again we have a negative slope. But this point right here, a little further on, we have a negative slope. But there's going to be a point where we move from having a negative slope to having a slope of 0, where we don't have any increase or decrease, where m, essentially m, where the slope of the tangent line is equal to 0. And then of course we're going to have an increase again, and an increase, and so on at any point on the line. But as we go down, as we move from decreasing slope, before we start increasing again, before our cost starts increasing again, there's going to be a point at which it's stationary. So if you imagine, for example, if you wanted to track the height of some ball, you would want to find the point at which it stopped increasing, the maximum height of some ball. We would have some ball that would rise, it would increase, and there's going to be some stationary point, and that stationary point where it, in theory, is not moving up or down at all, is going to be, in theory, its maximum height, and then it's going to start decreasing once again. Here we have decreasing slope. Here we've got a slope of 0, and then it's going to change direction. And if we find out where this slope is equal to 0, then by definition we found our minimum, because it's done all of the decreasing that it's ever going to do, and now it's eventually going to start increasing again. So where is the point where the slope is equal to 0, and what does that mean in terms of our derivative? All the derivative is, remember we call the derivative our slope function or gradient function. What that means is it gives us the slope of a tangent line at different points. It gives us the slope of the graph at different points. And what we're asking here is, okay, well, when is the slope equal to 0? We can put in different values of r. We can put in 1 or 10 and so on. But the question that we want to ask is, what is the value of r when this thing has a slope of 0? So set our derivative to 0, and this will find the minimum for us. When the slope is 0, we've reached the minimum. We've done all the decreasing we're going to do. We haven't yet started increasing. That's going to be the point where we have our minimum. Oftentimes these questions, if you have a derivative, sometimes it will be possible to use the original function, but oftentimes, especially on like a challenging paper too, where is something minimized or maximized? That is to say, where do you reach your maximum? Well, after you're done increasing before you start decreasing. And where do you reach your minimum? After you're done decreasing before you start increasing. So when m is equal to 0. So often when you see this minimize, maximize, set dy dx or f of x, whatever it happens to be, f prime of x, set it equal to 0, and then just solve. Essentially end solve, really. Okay, so there it is. When is the derivative equal to 0 for this function of negative 7.0r? We know that it's minimized. That is to say, we know the slope is going to be 0 when r is equal to 0.7. So when r is equal to 0.7 to the negative 2, I'm going to get a little more space. When r is equal to 0.7 to the negative 2 minus 14.08 over pi, and then r is again 0.7 to the negative 2 plus 2p, and then this is just pi. Is that all it is? 2p pi? Our derivative, no, it's 2p pi r to the 1. So r2 and then becomes 1. So 2 pi r, and then r once again is equal to 0.7. Okay. Now we've got an equation just in terms of p. Pi is not a variable, so it's just a whole bunch of numbers and then one variable p. And then what we want to do is we want to end solve for all of this. So let's go ahead. What we want to do is we want to end solve for p. Okay, so let's go into the calculator and work this out. This would definitely be one of those questions that you probably want to look over just to make sure that all of your numbers are correct. Negative 7.04 times 0.7, and we will raise the 0.7 to the power of negative 2. Brackets in this case don't actually matter. This is how I had written it. 0.7, essentially you just want the negative 2 applied to the 0.7. It doesn't matter in this case. Minus 14.08, set a fraction, 14.08 over pi. And then again, this is 0.7 raised to the power of negative 2, plus, I just realized I forgot to numerical solve this. There we are. Okay. 0.70 is good. -2 plus 2p times pi, and then r, which we know is 0.7. And then we want to ask the calculator to solve for, all of this is actually going to be equal to 0. So this is our derivative. 0 is equal to all of this business. And then we want the calculator to solve for p. So before I type this in, I'm actually going to just double check, just to make sure this matches written. So derivative of 0 is equal to -7.04, 0.7 to the power of -2, 14 pi, good, plus 2 pi, and this is 0.7 times p. Okay, there it is. It's fantastic. So find the value of p. P is the cost of this rectangular lid. So the cost of materials construct the minimized. Cost of materials to construct the container is minimized when the radius of the container is equal to r. So minimized, find the value of p. So we had just this p as an unknown. And therefore p is equal to 5.34622, or p is equal to 5.35. Okay, and then we can imagine it's dollars. Wow. Okay. Good question. Good question. Okay. Let's go on to question E. In total, 350 containers will be constructed at this minimum cost. Calculate the cost of materials to the nearest dollar to construct all 350 containers. Okay. So this is actually an interesting question. Calculate the cost of the materials to the nearest dollar to construct all 350 containers. So where is it? This is our cost function right here. We know what R is, and we can use that to find the cost. We know what P is, and we can use that to find the cost of a single container, and then we can multiply. That should work out okay. Yeah, it's a little unfortunate that a question which is, to be honest, not so challenging as an input-output if you just know your values and then multiply by 350 does itself depend on a previous question. I'm going to write this out just so we can substitute it in a little further below. R to the -1 plus 14.08 over pi r to the -1 plus p pi r squared. So this is a function which relates cost to the radius, and then of course it also has this value of p, which we do know now. Okay, so here we go. This is for part E. Calculate the cost of materials to the nearest dollar to construct 350. Okay, so we know what P is. We know R itself is equal to 0.7. So this actually isn't all that bad of a question, I suppose. 7.04 R is equal to 0.7. Raise that to the power of -1. 14.08 over pi. R is equal to 0.7 once again. Plus P, which we found out was 5.35. Times pi, and then this is just inputting this value of 0.7 in once again. So we know what P is, we know what R is, we have a cost which relates the cost of one cylinder to the radius, and then if we know P, we can just substitute that in. So that would give us the cost of one cylinder. So let's go back to the calculator and work that out. It's tempting to actually just grab this. No, I can't in this instance. Okay, so let's type it in. 7.04 times 0.7 raised to the power of -1 raised to the power of -1 plus, let's open up a fraction, 14.08 over pi multiplied by 0.7 raised to the power of -1 plus our value of p, which we found to be 5.35, multiplied by pi, and then 0.7 multiplied by 0.7 squared. And this is the cost of one cylinder, $24.69 and 54. So it's 24.6954. Let's write that out. Go back to the document here. Cost is equal to 24.6954. Cost is equal to $24.7. So $24.7 for one cylinder. And actually, let's keep all of our digits just because we haven't reached the final answer yet. So let's write it as 24.6954. Let's keep a fair bit of accuracy. That's the cost for one cylinder. But we don't want to know the cost just for one cylinder. We want to know the cost for 350 of these containers. So we want to take this, we want to take 24.6954 and multiply it by 350, and that will give us the total cost of the 350. So 24.6954 times 350. Whoops. 24.6954 times 350. 6954 times 350 equals $8,643.39. Here, once again, often not a bad idea to check, especially on paper 2, but in general, especially on financial mathematics questions or when it comes to monetary amounts, money amounts, nearest dollar. So $8,643. All right, that is how much it would cost for 350 cylinders. All right, 895. Let me just make sure this is all good. 6954. 6954 looks good. 54. Okay, good. Yeah, let's leave it. Let's leave that one just like that. I think that's good. Okay, question 5 continued. The materials for constructing the containers can be purchased at a discount according to the information in the table. Determine the cost of materials for 350 containers after the discount is applied. So they can be purchased at a discount according to the information in the table. Cost of the materials before the discount. So we know we paid $8,643. $8,643, which means that we would be within this range. Determine the cost of the materials for 350 containers after the discount is applied. Okay, so we have to pay $8,643, $8,643, but we have an 8% discount. So let's take away 8% of 8,643. If you're comfortable as well, 8% is equal to 0.08, and 1 minus 0.08 is equal to 0.92, or essentially 92%. So we only pay 92% of the price because we're taking 8% away. If you're more comfortable with this, either way, I'm going to go ahead and type in 8643 times 0.92. This is going to give us a value of $7,951.56. All right. Determine the cost 350 containers after the discount is applied. 3 sig figs, we would write this as 7950. Once again, 1, 2, 3. To be honest, a rather peculiar way to end a very complex question with a kind of simple discount, applying a discount. But overall, yeah, quite a good question, but a lot going on, certainly. Okay, everybody, I hope that was helpful. Remember, try to maximize process marks, look for entry points where they are. So, for example, just going back to this one, looking at the derivative, that will be something that will help. Writing this in terms of, so L is equal to something, and we can write this out if they give us the volume. That would be, another possible entry point. Looking at this, find the value of P. If we know what the derivative is, hopefully this should be okay as well. Finding the point at which our slope is equal to 0. They're a fairly common kind of question, when is something maximized, minimized. So looking for those entry points are always possibilities. Okay. Alright, everybody. I hope that was helpful, and as always, best of luck. Take care.